Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the force and torque acting on the walls of the container, or we can say the dam gates, because the dam gates bear some heavy amount of torque and force due to water, and due to that they experiences a large amount of torsion and stress. So that is a different part, but we are going to discuss the value of torque and force acting on the dam gates or container walls. So in this situation, you can see that there is a container which has a square wall. This is a square wall, and this wall is in form of a gate. It can open like that. This is the hinge, and this gate is being prevented from opening by this rope which is connected to this fixed wall. So we have to find out the tension in the rope. So first of all, let us see that what is the total force acting on this gate. You know that as we will move in the downward direction, pressure increases. Therefore, we have to integrate the elemental force to find out the total force. But one thing is very important, that when we are writing the pressure at this point, let us suppose that the depth of this point is y. So the pressure at this point will be P naught plus y rho g, but it is very important to note that the P naught is the atmospheric pressure, and the atmosphere is applying some force on this wall from outside also. So the outer pressure of atmosphere is also P naught. So we can ignore P naught, as the net force due to P naught on both the sides of the wall will be cancelled out, and the net force acting on the wall will only be due to the force of the liquid. So we have to consider an element for integration. Let us consider an element of width dy, and the depth of this element is equal to the depth of the wall, and the depth of the wall is h. So the force acting on this element like that, df will be equal to h rho g. In fact, this is y rho g into dA. dA is the small area. So dF will be y rho g into dA. Now dA will be dy into h. Small area will be dy into h. So dF will be equal to rho g h into y dy, and the total force will be the integration of dF, and it would be equal to rho g h integration of y dy. Limit will be from 0 to h. So total force will be equal to rho g h cube by 2. This will be the total force acting on this wall, okay, in this direction. Now we can say that the torque, if we talk about the torque, so to find out the torque d tau, let us consider a small torque d tau due to this df. So the torque of df about hinge point will be, this is h minus y. So torque of df will be df into h minus y, and the value of this df will be this one, rho gh into h minus y, this rho gh into y dy into h minus y. So tau will be equal to integration of d tau, and it would be rho gh and integration of y into h minus y dy. Limit will be from 0 to h. So now let us use the next page. So tau will be rho gh, and the integration of yh will be h into y square by 2, and that would be y cube by 3, and limit will be from 0 to h. So tau will be equal to rho g h to the power 4 by 6. You can check this expression, and I have seen many students are calculating the tau by applying this total force on the center of mass of the wall and multiplying that force with L by 2 or H by 2. So you can see that this is an incorrect approach because force is not uniformly distributed on the wall, and this F, if you multiply this total force rho g h cube by 2 by h by 2, then the expression of torque will not be the correct one. You can see that this is the correct expression of torque. So you should always remember that to find out the torque, you have to integrate the elemental force and elemental torque acting on a small element of the wall about hinge. So this is the first thing which is very important to note. And in this case, if we have to find out the tension, then we can say that the torque of tension is preventing this gate to open. So the torque of tension will be T into H. So it would be equal to rho g h to the power 4 upon 6 will be equal to T into H. So T will be equal to rho g h cube by 6. This will be the value of tension. Now if we talk about a trick to find out the force acting on the wall or any object immersed in the liquid, then we can say that if this is a small area, and let us suppose that this area is A, and we have to find out the total force acting on this area. So let us suppose that there is a small elemental area in this area which is dA, and the force dF acting on this element will be, if the depth of this element is y, so it would be y rho g, this would be y rho g into dA, and the total force acting F total will be integration of dF, and F total will be integration of, we can say that it would be rho g into integration of y dA. Now we know that the center of mass coordinate ycom will be integration of y dm, so it would be y dm will be equal to sigma into dA, small area, where sigma is mass per unit area, upon integration of dm, which is sigma dA. So cancelling this sigma with sigma, you can see that ycom into integration of dA will be equal to integration of y dA, and this is total area, so ycom into total area will be equal to integration y dA. So we can, in the expression of total force, we can replace y dA by this one. So we can say that the total force F total will be equal to ycom into rho g into area, and this is the pressure this is the pressure acting on the center of mass of the immersed object. So this is PCOM into A. What I am trying to say is the fact that if you have to find out the total force directly, you can find out the pressure at the center of mass of the wall or object, and you can multiply the area of that wall or object with that pressure at center of mass. For example, in this case, what we can do to find out the total force is the fact that we can find out the pressure at the center of mass of this wall, and the pressure at the center of mass of this wall would be h by 2 rho g, and we can multiply the area of the wall h square. So it would be h square into h by 2 rho g. So it would be rho g h cube by 2. Okay, and now I'll demonstrate. Now I'll demonstrate another example of this fact, this trick, that there is, let's suppose that there is a triangle, equilateral triangle, and this triangle is having the side A by A by A, and this triangle is being immersed in a liquid like that, and the obviously net force acting on this triangle will be 0 because liquid will be pushing this triangle from both the sides, therefore net force will be 0. But if we need to find out the force acting on this triangle from one surface or one face, so force on one face will be easily calculated without integration by using that trick. So we just need to find out the center of mass of this triangle, which is obviously the centroid, and the depth of this center of mass is y. Y can be easily calculated according to the situation. So you can say that the pressure at center of mass is y rho g, and the area of triangle is A. So the force on any one surface of this triangle will be this pressure at center of mass into area of the triangle. Now if in this situation a container is having two liquids of different densities partially filled, and let us suppose that this is H by H wall and this is again H by H wall, and we have to find out the total force acting on this wall, this complete wall. So let us suppose that the force acting on this wall is F1 and the force acting on this wall is F2. So F1 will be the force acting on this wall. So it would be equal to the pressure at center of mass of the wall, which is H by 2 rho 1 g, and multiply by the area, which is H square, and the F2 will be the pressure on the center of mass of this wall. Now pressure at center of mass of this wall will be the complete pressure due to this liquid plus the pressure due to H by 2 height of this liquid. So the complete pressure at the center of mass of this wall will be equal to rho 1 Hg plus rho 2 H by 2g into the area of the wall is H square. So the total force acting on the walls will be F1 plus F2, and if you will add up these forces, then you can say that it is 3 by 2 rho 1 g h cube plus rho 2 g h cube by 2. This is the total force acting on this wall. And now in this case you can see that if the wall of the container is tilted like that, then we can easily say that the force acting on this container would be like that, F. And therefore there will be two components of this force, Fx and Fy, and Fx and Fy are the x and y components of the forces, and we can find out the x and y component easily by using a simple analogy that if let's suppose that this is area A2 and this area is A1. So we can say that Fx will be equal to the pressure at COM PCOM into the area A1, and Fy will be equal to PCOM into area A2. So PCOM will be H by 2 rho g. So Fx will be equal to H by 2 rho g into A1 area. Now A1 area, now depth of this wall is L. Depth is L. So A1 will be the height, this height is H. So A1 will be H into L. H into L. And in this case it would be H by 2 rho g, and this A2, this length is L, this is L, and this length is L cos theta. So it would be L cos theta into depth is again L. And H can be written as H is also equal to L sin theta. Okay, so this is the trick to find out the force. Now in this case, if the shape of the wall is arbitrary, this is an arbitrary shaped wall, so we have to consider a element, and the force acting on this element is dF. Now again, if we wish to find out the two components of the force, dfx and dfy, so again if this total area is A1 and if this total area is A2, then Fx total will be equal to, or dfx will be equal to dfx will be equal to the dA1 small area perpendicular to dfx multiply by pressure, which is P at this position. So again Fx will be equal to the area A1 into P at COM, and Fy will be equal to area A2 into P at COM. So what I'm trying to say is the fact that there would be no effect of this arbitrary shape of the wall. In fact, we have to use the same method which we used in the previous case. Okay. Now let us discuss the reaction of the base reaction on the base of the container. है ना? Now you can see that there is a container having some liquid of mass m. Now the mass m in this container will be equal to h into a into rho, and mg will be equal to g. And the pressure at this point will be pressure due to liquid. I am not considering the atmosphere because atmosphere will be applying the force from downward also, so that would be cancelled. So pressure due to liquid will be equal to h rho g. So force on the base of the container will be equal to h rho g into area, and you can see that this force is exactly equal to the mg of the liquid. So we can easily relate that the force on the base of the container will be equal to the pressure of the liquid into area, and that would be equal to the mg of the area. Now let us consider the second case. In this second case, the mass of the liquid will be equal to, you can see that is, let us suppose that this is A, this area is A, and this area is 2A. So the total volume is 3AH, and mg will be equal to, this is into rho, so mg will be equal to 3AH rho g. So the total mg of the liquid in the container is 3AH rho g, and the pressure at 0.5, 4 and 6 will be equal to 2h rho g. You can see that this height is 2h, so it would be 2h rho g, and we are again ignoring the atmospheric pressure. So we can say that force on the base of the container will be equal to 2h rho g into area, which is 2a. So the force on the base is 4ha rho g. Now there is a contradiction in this case, as the mg and the force on the base are different. So why the force on the base acting on the container is greater than mg? Let us discuss this point separately. So let us draw this, let us use another page. Let us use this diagram on the next page. So in this case, you can see that the pressure at point 3, pressure at point 1 and pressure at point 2, these 3 points, is equal to h rho g. And this pressure is being applied on the roof of the container, and let us suppose that force acting on the roof is F, like that. So this remaining area, this total remaining area is A. So force will be equal to h rho g A. Now the liquid is applying this force on the roof in the upward direction, and the roof will be providing the reaction of this force in the downward direction. So reaction will be equal to F, and it would be h rho g A. And that force acting on the base of the container will be mg plus this reaction, because finally this reaction would be transferred to the base only. So force acting on the base will be equal to mg, and mg is this one we have already written. It is 3ha rho g, and this reaction is R is h rho ga, so it is 4h rho ga. So therefore the force acting on the base of the container is greater than mg. So in this case, you can see that if in this shape of the container, the force acting on the base will be equal to the mg of the liquid. But if the container has this shape, this one, and liquid is being filled in the container, then the force acting on the base, F base, will be greater than mg, because the force applied by liquid on the walls will be like that, and reaction will be like that. So a y component of reaction will be added up, and it would increase the force on the base. But if the container shape is like that, so you can see in this case the force acting on the walls is like that and the reaction will be acting like that. So the force acting on the base will be reduced by mg. So guys, this was it in this video, and in the next video we are going to discuss we'll be discussing the problems, concept illustration problems based on this concept. Thank you.